Hello everyone, I'm Ryan and we are Group 31. Our project is on autonomous maze navigation using reinforcement learning. And these are all my group members. Project background. As for our project background, reinforcement learning is a paradigm for sequential decision making where an agent interacts with an environment, takes actions, and receives rewards. Our maze solving problem can be naturally cast as a RL task. The agent starts in one corner, moves around the grid, and aims to reach the goal while avoiding walls. We'll show how this maps to the MDP formalism, states actions, transitions, rewards, and terminations. In this project, we implement two solutions approaches. First, classic tabular queue learning, which keeps a lookup table for queue values for every state action pairs. And second, a deep queue network, where a convolutional neural network approximates those queue values. Comparing them highlights the trade offs between simplicity and scalability. Our project significance. Why is this important? Educationally, our maze solver gives the hands on experience with the core RL concepts exploration versus exploitations, reward shaping, convergence behavior. It's also a clean benchmark for tuning hyperparameters and can be extended to dynamic mazes. Finally, it lays the foundation for advanced topics like hierarchical RL and multi agent coordinates. Beyond academics, autonomous navigation has a real world impact. Warehouses, robots, and delivery drones use path planning to navigate aisles. AGVs in factories optimize routes to minimize the travel time. Video game NPCs require efficient map traversals. Even network routing can be cast as a maze like graph problem. Our work ties directly into these domains. Introduction. Our core task builds an R Our core task is to build an RL agent that learns to navigate a grid maze from a fixed start to a fixed goal. We model the maze as a MDP and let the agent discover through trial and error. The policy that maximizes cultivates reward. Along the way, we contrast tabular and deep learning methods.
Markov decision process. So let's begin by understanding what MDP is. A Markov decision process is the core mathematical framework behind reinforcing learning. It consists of five elements: states, actions, transition probabilities, rewards, and discount factor. These components allow us to make model decision making problems where outcomes are partly random and partly under control of the agent. Mapping the MDP to our maze project. Here we map each MDP component to our custom maze environment. State S correspond to the agent's current location of the grid. Actions A are the four possible movements up, down, left, and right. P transitions are deterministic. The agent only moves if the cell is valid or free. R is rewards, which is guide behavior, small penalty, larger penalty, and positive reward, which is +1 for reaching the goal. The episode terminates either when the goal is reached or the step count exceeds the limit. Maze environment. The slide shows how maze environment is initialized in code. It creates a square grid of size n with the start position at the top left, 0, 0, and goal at the bottom right. The movement options are defined using the direction vectors. Rewards for valid steps, hitting walls, and reaching goals are also initialized. The maze can be randomly generated or loaded from a predefined data for consistency in experiments. Step function. This function defines what happens when the agent takes a step. It calculates the new position based on the selected action. If the move is valid and doesn't hit a wall, the agent updates the position. Rewards are assigned based on the result. Default is the step penalty. Overwritten if the agent hits a ball, -0 0.5, or reaches the goal is +1. So this function effectively encodes the S, comma A gives to S dash R transition in the form of MDP. Here's what the environment looks like visually. The green cell is the starting point and the red cell is the goal. Black cell represents the wall agent can pass through. The agent is represented in blue, and its path will be shown as moves. Why does the MDP rule matters? Framing our maze as an MDP is essential because it allows us to apply algorithms like Q learning and deep Q networks. The MDP abstraction ensures we clearly define the state, action, transition, and rewards and mechanics. By comparing our RL agents learned policy against the optimal BFS paths, we can objectively evaluate it.
Q-learning is a model-free off-policy algorithm that learns a value function Q, representing the expected cumulative reward of taking action and following the optimal policy. Its steps include initializing the Q table, interacting with the environment, and updating Q values using the Bellman equation. The Bellman equation is basically a way to figure out the best value of taking an action in a situation by looking at the current reward plus the best possible future rewards. Here's the implementation of the Q-learning agent. It's initialized with parameters like learning rate, discount factor, and exploration rate. The Q table starts with zeros for each state action pair. The select action method uses epsilon greedy with probability exploration rate. It explores randomly, otherwise it exploits the best Q value. The update Q table method applies the Q-learning update rule to adjust Q values based on rewards and next states. The training loop runs for a set number of episodes. For each episode, the agent starts from the initial state, selects actions using epsilon greedy, and updates the Q table based on rewards and next states. We track total reward, steps, and success rate per episode. Every 100 episodes, we print progress, showing success rate, average steps, and exploration rate to monitor learning. After training for 500 episodes, the results are clear. Total rewards start negative but improves to nearly zero, indicating efficient goal reaching. Steps drop from over 175 to around 30, showing the agent learns shorter paths. Success rate reaches 100% by episode 300, proving that the agent has mastered the maze. Here's a visualization of the learned path. Starting from the top left, the agent navigates around walls to reach the bottom right goal in 26 steps, the shortest possible. This demonstrates that Q-learning has successfully learned an optimal or near optimal policy for our maze. We chose Q-learning for its simplicity and effectiveness in small environments. It's model-free, so the agent learns the maze's transition probabilities through trial and error, which is ideal for our custom maze environments. For small grids, Q-learning guarantees convergence to the optimal policy, providing a reliable baseline to compare with DQN. Additionally, its update rule is transparent, making it perfect for demonstrating key concepts like exploration versus exploitation and reward shaping. It also has low computational overhead. For smaller mazes where the Q table is small, the algorithm runs in milliseconds per step, which lets us quickly tune hyperparameters like learning rate and exploration rate. It acts as a benchmark to evaluate DQN's performance in terms of convergence speed, path optimality, and sample efficiency.
Okay, now I will show why we use deep Q networks for our maze navigation project. DQNs extends Q learnings by replacing lookup tables with neural networks to approximate the action's value function. This innovation let us scale to larger environments where storing all stage action pair is impossible. Because key DQN's components includes function approximation using CNNs, experience replay to break temporal correlations, and a separate target network for stability. Our next slide shows that is our network definition. Our networks architectures take a 3-channel input representing maze layout, agent position, and goals position. It processes this through 2 convolutional layers and 2 fully connected layers to output Q value for each action. For action selection, we implement an epsilon greedy policy, sometimes exploring randomly, otherwise exploiting the highest value action predicted by our network. Our next slide shows that this is our training process for the maze project. It has sample transition from our replay buffer. It computes current Q values from our policies network, calculate target Q value using the Bellman equation. It also updates our network to minimize this difference periodically since our target network with the policy network. The next slide shows that this is our training result. Our training metric shows the DQNs gradually improving but facing challenges. By episode 200, it reaches only 20% success rate. This visualization shows our complex test maze with a 26-step optimal solution, but the DQN struggle to consistently navigate to the goals. Why use DQNs? Despite challenges, DQNs offer compelling advantages over Q-learning. It has a larger scalability to a larger environment. You also learn from visual input without manual features engineering. Architectural flexibility for 3D maze or real-world scenarios. It also has pattern recognition that generalize to unseen environment. Our next slide shows that this is our comparative result for Q-learning and DQNs. The Q-learning has 100% success rate while it has 26-step average, which is optimal, and 0.75 average reward, while DQN achieved only 0% success rate, 200 steps average minimum, and negative 2.0 average reward. The DQN exhausts our step limit without finding the goals, accumulating only penalties. In conclusion, Q-learning works exceptionally well for small, discrete environments, while DQN show promise for scaling to complex spaces but require more tuning. By using Q-learning as a reliable baseline for small MDPs, we will also adopt DQN when generalization to high-dimensional spaces is needed. Our future work includes reward shaping, prioritize replay, and extending to 3D environment and robotic application. Thank you very much.